All right, so Chapter 12, Chemical Kinetics. What is chemical kinetics? Kinetics is all about motion. So kinematography is moving pictures. Kinesiology is the study of the movement of the human body. I was confused back in grad school when one of my first students said she was studying kinesiology. Turns out that meant she was going to be a dancer. And then kinetic energy, of course, is the energy of moving objects. So chemical kinetics is all about how particles, objects, molecules, and atoms move, and how that determines and affects chemical behaviors, mostly when you are talking about chemical reactions. So let's talk about the rate of a chemical reaction. A lot of the time you want chemical reaction to go faster. Sometimes you need it to go slower. So it helps to know how to measure the rate of a chemical reaction. It is the change in the amount of one of the substances over time. That's really all there is to it. You can measure it in concentration over time, the change in concentration over time, or the change in mass over time, or the change in pressure over time if you're talking about a gas. So when you actually write it out, it looks like this down here below. The rate of consumption for reactant A is negative delta concentration of A over delta T. For D, it's delta D over delta T. That negative sign is important. Okay? The rate of the reaction needs to be positive. So because A is disappearing, it's going to have a negative change. So you multiply it by that negative sign to make the rate positive. Okay? And that is, in a nutshell, how you measure the rate of a chemical reaction. It is relatively straightforward in that way. Now, when you look at the rate of a chemical reaction, the speed at which A is consumed is going to be different from the speed at which D is produced, just because of the coefficients in front of them. So when we talk about the rate of reaction, what we're actually talking about is the relative rate of reaction, where we go ahead and we divide by the coefficient for each reactant. And that way you get the same relative rate for each reactant and for each product. Okay? So the relative rate for this reaction is just negative 1 over A times delta A over delta T is going to be equal to negative 1 over B times delta B delta T is equal to 1 over C times delta C delta T is equal to 1 over D times delta D delta T. Okay? That means that whenever we're talking about the rate of reaction, we've always normalized it so that the number we're talking about is always the relative rate of reaction, not the rate for each particular reactant or product. Now, as for what determines or what affects the speed of a reaction, there are a number of these things, and you can get very detailed and complicated, or you can just do a surface view of those. We're going to stick largely to the surface. The factors are the chemicals involved in the reaction, the surface area, temperature, the concentration, and the presence of a catalyst. Now, the chemicals involved, that's kind of a duh, Different chemicals are going to react at different rates, Very similar chemicals might have very similar reaction speeds, or they could have wildly different reaction speeds. Just because they're going to have different structures, they're going to move at different speeds to explore the space they're in. They can be a number of things going on in there. But you need to go ahead and get that out there. Just different chemicals equals different reactions. Next up is surface area. Surface area requires a little bit more work to get at, but not much. If the chemicals can't actually interact, if the molecules themselves can't hit one another and react with one another, then they're not going to react. Okay? They actually have to be touching. So surface area means that the things have to be touching, basically. So if there are different phases involved, then you can increase the reaction rate by increasing the area where the phases are touching. So here we have a couple of examples of different phases involved in a reaction. Up top, we have a liquid and a gas. The only place they can react is where the gas and the liquid are touching. So one way to increase the surface area is just to make the container of the liquid wider. And that'll increase the amount of surface that the gas can touch. Another way is to bubble the gas through the liquid. Then you have lots and lots of tiny little bubbles, each of which has a lot of surface area. Down at the bottom, we have an example of a solid. A solid will react more quickly if you break it up into smaller pieces. Okay, so you have a big cube starting out there on the left, and you break it up into a lot of little cubes, and all the stuff that was locked away on the inside is now available for reaction. That's why if you try to light a log on fire, it's really, really difficult. But if you grind that log up into sawdust, it's very, very easy to light that on fire. Back at the beginning of the industrial age, they had a lot of problems with that. Of course, I'm referring to the beginning of the industrial age here by talking about Roman times. They made extensive use of rivers, Romans did. And later on, after the Dark Ages, so did the rest of medieval Europe. Extensive use of rivers for mill work. They had wood sawmills and grist mills for grinding grain. And they were absolutely forbidden to work at night because any light meant an open flame, and an open flame meant explosive fiery death and the destruction of the mill. So they could only work during daylight hours. Other mills that didn't involve the creation of fine powders like that, they could work at all hours, and sometimes they did. And our next factor is temperature. So when temperature is higher, particles are moving faster. Temperature is a measure of the average kinetic energy. So when they're moving faster, one way to talk about that, we say they sample space faster. Because, as they're moving, they're bouncing randomly off of other particles nearby. Remember from kinetic molecular theory, talking about gas. The same is true of a liquid, albeit at a slower pace, just because liquids are denser and lower temperature, typically. But they're still sampling space. They're exploring the space around them. If they're moving faster, they're able to do that exploration faster. So they're more likely to encounter the things they need to encounter in order to react. The other thing is that because they're moving faster, the individual particles are likely to have more energy. They're likely to have enough energy to react. We'll get into this more a little bit later, but just running into one another isn't enough to make the particles react. They have to be able to get over an energy barrier. They need to have enough energy. So all told, when you are talking about temperature, every additional 10 degrees of temperature is a doubling of the reaction rate. So 30 degrees is twice as fast as 10, or as 20 is twice as fast as 10, is twice as fast as 0 degrees Celsius. And here we have concentration. Well, this is mostly straightforward, but mostly not. A higher concentration just means you have more stuff present. If there's more stuff present, then it's more likely to find the other stuff that it needs to react with, and it's more likely to react. Now, the reason it's not a simple and straightforward ratio is that the more A there is, if you're talking about A needing to react with B, the more of A there is, the more likely A is to run into B and react. But the more A there is, the more likely A is to run into A and not react. So it's not an entirely straightforward and simple measurement. But in general terms, the more you have of your reactants, the faster the reaction is likely to go, in most cases. And finally, we have our catalysts. Okay, a catalyst is a substance that increases the speed of a reaction, but it is not consumed in the reaction. So it's in the reaction, but not of it, to steal from the evangelicals. When we write the chemical reaction, we will often write the conditions of the reaction above and below the reaction arrow. So for example, here we have, just generic A going to B requires some catalyst. We might just say that it requires a catalyst. Or we might specify what the actual catalyst is. It might be catalyzed by an acid or a specific compound. Down here at the bottom, I've sketched out the reactions involved in the catalytic converter. Just the uncombusted fuel and various nitrate byproducts, nitroxide byproducts, all nasty and toxic, are broken down thanks to the presence of platinum, which converts them into CO2, H2O, and nitrogen, and thus eliminates nasty, nasty smog. Catalysts are very useful. Our bodies make heavy use of catalysts, although when they're organic and made out of proteins, they're usually called enzymes. For example, coming back to this slide, your saliva contains an enzyme called amylase, which breaks down complex carbohydrates into simple sugars. That's why, if you hold a saltine cracker in your mouth for long enough, it'll start to taste sweet. Not because there's sugar hidden inside the cracker, just that you've actually started to digest it there in your mouth. This is beginning to be a big part of research for chemical synthesis and so on, because catalysts make reactions a lot easier. You don't need the big, powerful, noisy machines, so less energy just makes it cheaper overall. And that's where we're going to leave catalysts. We're not going to go into too much detail on those. We'll cover them now with talking about activation energies. Okay. We won't go into the detail that is at the end of the chapter, but here we have a picture of a reaction coordinate, and the vertical axis is energy. Okay. Reaction coordinate just means how far has the reaction proceeded. It's a theoretical concept that you could think of it as applying on the scale of individual molecules reacting, but it's more a way to describe reactions in general rather than a description of the actual reactions themselves. So on the left here, we have an uncatalyzed reaction, going from reactants R to products P. Okay, the products are lower in energy than the reaction, so this is an exothermic reaction we're looking at. But in order for the reactants to become products, they have to have enough extra energy to get over this barrier. And the difference in energy between the reactants as they are and the top of that peak is known as the activation energy. Okay. And that's why higher temperatures mean the molecules are likely to have enough energy, because they need extra oomph. They need that extra push to get over that barrier. And at higher temperatures, they're more likely to have that energy. Lower temperatures, they're less likely to have that energy. A catalyst operates by decreasing the activation energy. It can, just make it that much easier for the reaction to proceed. So here on the right, we have the same reaction, but with the presence of a catalyst, and it's just lowered that energy barrier in one way or another. Catalysts can operate in a number of different ways. And that just means that it's easier to get from reactants to products. And it works the other way, too, if you have an endothermic reaction. Like if you were going from products to reactants, the presence of a catalyst also makes that reaction easier. So catalysts don't care about which way you're going. They just lower the barrier either way. Okay? A smaller hill is a smaller hill no matter which side of the hill you're standing on. And that is activation energy. Definitely remember that. We'll touch on it again a bit later. But we will be saving all of that and more for our next lecture, because we are bumping up on the 15-minute mark, so we're going to stop lecture 1 here.